Here we have an object moving in a circular path. We have this little blue guy right here starting at position 1 and wrapping around to position 2. And when it does that, it will travel this distance across here and sweep out this angle. I've also labeled the radius of the path for the two locations, and we've got a couple velocity vectors, velocity 1 and we've got velocity 2, and you can see the two velocities, of course, are tangent to the actual circle. Now, by looking at the diagram, you can see that velocity 1 and velocity 2 are not equal to each other. Now, they do have the exact same magnitude. They're the same size, but they have different directions. Now, because they have different directions, the two velocities aren't the same, which means we actually have to have an acceleration. Now, most people, when they think about acceleration, they think about going faster or slower, which would be the magnitude, but that's not what's going on here. The acceleration is purely being used to change the direction of the actual object itself, creating the circular path. Now, this is what is often called centripetal acceleration. So let's see if we can actually do a little derivation and analyze the situation a little bit to see what's going on to actually create the centripetal acceleration and how to calculate it. So to analyze the situation, we're going to specialize this a little bit up here. Again, we're going to have 2 points, except we're going to have these 2 points unbelievably close together, like infinitely close together. Now, we can still draw and label the exact same thing, except it becomes a little more difficult. For the radius, I could still draw the radius like this, but when I draw the second radius, it'd be very, very, very close. So really, really hard to see. So what I'm going to do is I'm going to exaggerate the radius so we can actually see it a little bit more clearly. I'm going to do the same thing for the other one. I'm going to draw the radius, but again, instead of drawing the radius there, I'm going to exaggerate it and spread out to the side so we can actually see it a little bit more clearly. Now, once again, I can label the stuff that we have on here and exactly what's happening. We have an angle that was swept out, and of course, it will have traveled that distance across. Of course, exaggerated, but now we can actually see what's going on. Now I can do the exact same type of thing with the velocity vectors that were on the top. Again, I'm going to start with the two blobs really, really close together. And now what I'm going to do is I am going to draw my velocity vectors. But again, instead of drawing my velocity vector tangent to the circle, I'm going to exaggerate it more so we can actually see it. And then I will do the exact same thing for the second one, unbelievably close together. But again, instead of drawing a tangent, I'm going to exaggerate it, maybe something like this. So now I have my two velocity vectors, right, like that. Now, when I do that, the actual angle that is swept out here in my radius and D diagram is the exact same angle that I get here between my vectors. And over here, I've got a nice isosceles triangle with my two radii, and then a nice D value to finish off the triangle. But I can actually do the exact same thing with my velocity triangle. I've got the angle right here. I've got two V's which are the same. So again, an isosceles triangle. And if I would connect the ends like this, I will create another triangle part that's actually the change in velocity. It's the difference between the two velocities. So what I've created are two triangles. I've got two isosceles triangles, a D triangle and a V triangle. Now, since those two triangles are both isosceles triangles and they have the same angle, what I've actually done is I've actually created two similar triangles. Now, since those two triangles are similar to each other, they are going to have the exact same proportions, ratios for angle, sides, whatever you want. They're not congruent, they're not the same size physically, but everything's going to be similar and match up. So since they are similar, what I can do is I can use ratios to equate them and connect the two things together. So that's what we're going to do is we're going to set up a ratio. So I'm going to have something is equal to something. Now I'm going to match up the sides. Now, what I'm going to start with first is the side opposite of the angle. Now, if I go to the angle and opposite of that, I've got the D value in my first triangle. So that's going to be my D value. Now, that matches up to the side which is opposite to the angle in my second triangle, which would be my delta V. So that's going to go over here. Now, the only thing I need next for my ratio is to take another side. Now, I can take this radius, it doesn't make any difference. They're the same radius. So I am going to put the radius over here, and to match that up with a length on the other triangle, maybe that one, doesn't make any difference. That, of course, is just a velocity vector. And now I've actually made a ratio which connects my two triangles using the sides, which would be totally similar to each other, so we get the exact same ratio. Now, when we're working with acceleration, typically it's the change in v that you're concerned with. Usually it's delta v divided by delta t. So let's see if we can rearrange this and focus in on that change in v. So if I rearrange the expression, change in velocity would be d times average v divided by r. Now, if we go back to the more traditional expression for acceleration, which is change in v divided by change in t, I can take my new expression and substitute it in with the old expression, substitute then for the change in v. Now, if I do that, I end up with d times v divided by delta t times r. And as soon as I do that, these two quantities go really nicely together because, of course, d divided by t is another way to calculate speed or velocity. So I actually have two speed and velocities here, one inside of this combination and one right here. So if I simplify this even further, it ends up being v squared divided by r. Now, most people don't treat this as velocity. Most people treat it as speed because the direction is always changing, and you end up with a nice expression for centripetal acceleration, which is v squared over r. Now, AC equals v squared over r is the way to calculate how big the centripetal acceleration, but what about the direction? It is a vector quantity and does have to have direction. Well, the direction of the acceleration and the direction of the change in velocity, they have to have the same direction because it's the acceleration which actually creates the change in v in the first place. So they actually always go in the same direction. So let's go back to the diagram. And again, we can draw a couple circles and stuff like that. No big deal. So we'll draw a couple circles again. And let's look at the velocity vectors to see what they're doing. Now, when we draw these velocity vectors, we are going to exaggerate them again. It doesn't make any difference. But what we're going to do is we are going to redraw them. So now, if we look at the classic way to find change in velocity, change in velocity is v2 minus v1. I mean, that's an old-fashioned way to calculate change in velocity. Now, we can do this just by using good old-fashioned vectors. We just draw vectors. Now, if I draw v2, that would be this guy right there. If I draw v2, it would look something like this. And then what I need to do is I need to subtract v1 from it. Now, if I was going to add v1, I would add v1 and it would look something like this. But I don't want to add it, I want to subtract it. So it would go the exact opposite way and go something like this. And that is how I could draw v2 minus v1. Now, if that's v2 minus v1, then going from beginning to end, from here to here, that is the answer or the change in velocity. This is just basic grade 11 vector analysis. Now you can see from this that this change in velocity vector is going straight down, pointing towards the center of the circle. And that's exactly the direction the centripetal acceleration goes. It always goes to the center of the circle. Okay, so v squared over r is how we can calculate how big it is, and the acceleration direction is always going to the center of the circle. And remember, these points are arbitrary. They can be anywhere on the circle, and it doesn't matter which locations you use, you'll always get a change in velocity and acceleration pointing to the center of the circle. Now, this is really, really important because of this, the centripetal acceleration is always perpendicular to the velocity. And this is why it cannot change the magnitude of the velocity. It can't make it going faster and slower. In order for that to happen, it would have to be parallel to it, or at least partially parallel to it, but it's not. So since the centripetal acceleration is always perpendicular to the velocity, it can only actually change the direction, and it can't actually change how fast or slow it is.